So I'm going to talk about homogenization of the periodic Schrodinger-type equations. And let us start with the statement of the problem. And first we introduce some notation. By gamma, we denote a lattice in RD. Omega is the cell of this lattice. Gamma tilde is the dual lattice, and omega tilde is the central Brillouin zone of the dual lattice. For instance, if gamma is the cubic lattice, ZD, then omega is the unit cube. Gamma tilde is also cubic, 2 pi z to the power d, and omega tilde is the cube minus pi to the power d. Next, we agree to use such notation. Epsilon is a small positive parameter, and for any gamma periodic function, we denote by f epsilon of x, f of x over epsilon. So for small epsilon, such function oscillates rapidly, and homogenization theory studies differential equations with such coefficients. Now we introduce our main object. It is a second order elliptic operator, A epsilon, acting in the space L2 RD Cn. So it's L2 space of Cn valued functions in RD. And we assume that the operator A epsilon is given in a factorized form. B of d star, G epsilon of x, which is G of x over epsilon B of d. Here, the function in the middle is a matrix-valued function of size m by m. B of d is the first-order differential operator, the sum of bj dj. And bj are matrices, so it is of size m by n. The adjoint operator is of size n by m, so A epsilon is n by n. And it is assumed that m is greater or equal than n. Next, our assumptions about g of x. G of x is gamma periodic, matrix-valued function. It is bounded and uniformly positive definite. In general, it is a Hermitian matrix with complex entries. So we do not need any smoothness assumptions. Only G is bounded and positive definite. B of d is the first-order differential operator with constant coefficients. Bj are also matrices in general with complex entries. We consider the symbol B of xi of this operator B of d and assume that it has maximal rank. The rank of the symbol is equal to n for any non-zero vector xi. Under such assumptions, our operator is strongly elliptic. Of course, the precise definition of this operator is given in terms of the corresponding quadratic form given by this integral on the Sobolev space H1. It is non-negative and closed. In fact, under our assumptions, A epsilon of u satisfies such two-sided estimates. So our operator is strongly elliptic. The simplest example is the acoustics operator. It's a usual divergence type operator. In this case, this B of d is simply d, so it is a column. And in this case, n equals 1. That is why we call it the scalar case. The operator acts on scalar functions. And m is equal to d. For example, the operator of elasticity also can be written in such form. So we have other examples. What is our problem? We wish to study the behavior of the operator exponential for a epsilon. Tau is a real valued parameter. It is time. We wish to study the behavior of this exponential for any tau and for small epsilon. We will formulate the results in the operator terms, but of course we can apply the results to study the behavior of the solution u epsilon of the Cauchy problem for this Schrodinger-type equation with the following initial condition. Obviously, the solution can be written as this operator exponential applied to phi. So from the results for the exponential, we can easily derive the results for this solution. We show that in some sense, this exponential behaves like the exponential for the operator A naught, where A naught is the so-called effective operator. It is also given in such factorized form, but now G naught is a constant matrix, which is called the effective matrix. And we recall the definition of G naught. This definition, of course, is well known in homogenization theory, but it is non-trivial. In order to define the effective matrix, first we have to consider the so-called cell problem. This is cell problem. By lambda of x, we denote the matrix valued gamma periodic solution of this equation. It is an elliptic equation on the cell on omega with periodic boundary conditions. And we fix the solution by this condition. The mean value of lambda is equal to 0. Next, we define the matrix valued function g tilde of x in terms of lambda, given by this expression. And its mean value is G naught, the effective matrix. It turns out that the effective matrix is always positive definite. And now it will be convenient to give a short survey. I will speak only about operator error estimates, not about the classical results. And let us recall what is known for elliptic and parabolic problems. In 2001, in our joint work with Mikhail Solomonovich Birman, the operator theoretic approach to homogenization was suggested, and it was proved that the resolvent of A epsilon converges to the resolvent of the effective operator in the L2 operator norm. And the norm of the difference satisfies estimate 1, estimate of order epsilon, which is order sharp. In our next paper in 2005, a more accurate approximation for this resolvent was obtained, also in the L2 operator norm, but now the error is of order epsilon squared, and the operator k of epsilon is called a corrector. I will write down this operator. And finally, in 2006, approximation for this resolvent in the energy norm was obtained. Here we take the norm from L2 to H1, which is often called the energy norm. And here error is of order epsilon. And K1 also is called corrector, but these correctors are different in estimates 2 and 3. Now we define the characters, and first we define this K1, which is more or less standard character known in homogenization theory. Here it is. This character involves the resolvent of the effective operator, the differential operator B of D. Lambda epsilon is multiplication by the rapidly oscillating matrix-valued function, lambda of x over epsilon. And also here we have pi epsilon, which is the smoothing operator, and it plays auxiliary role. This is pi epsilon. U hat is the Fourier transform of U, and it looks like we take the inverse transform, but we integrate not over RD, but over this large set, omega tilde divided by epsilon. This is the smoothing operator. Note that this term, epsilon multiplied by K1, is of order 1. It is not small in this norm from L2 to H1. It is of order 1 because when we calculate H1 norm, we have to take derivative of the rapidly oscillating function lambda epsilon. And so K1 itself is of order 1 over epsilon. So this term is of order 1, but the difference is of order epsilon. And in estimate 2, this term is of order epsilon in the L2 operator norm. The difference is of order epsilon squared. The character K is more complicated. It is the sum of 3 terms. This K1, the adjoint of K1, and also the third term K3, which does not depend on epsilon, and now I prefer not to write it down. Similar results were obtained for parabolic problems. We consider this parabolic semigroup and show that it converges to the semigroup for the effective operator in the L2 operator norm. And again, the error estimate is order sharp, order epsilon. A more accurate approximation with error of order epsilon squared was found by Lisa Vasilievskaya in 2009. K is the corresponding character, which is similar to the elliptic character. And also, approximation in the energy norm was obtained, the norm from L2 to H1, and error of order epsilon. Such estimates are called operator error estimates in homogenization theory because they are formulated in operator terms. And a different approach to such estimates, the so-called shift method, was suggested by Vasily Vasilievich Zhikov and developed by him jointly with Svetlana Pastukhova. In fact, they wrote many papers, a big series of papers, and I would like to mention a survey by Zhikov and Pastukhova in 2016, published in Russian Mathematical Surveys. A survey about operator error estimates. And now let us discuss what can we say about non-stationary problems, about Schrodinger-type equations and hyperbolic equations. The situation is different from the elliptic and parabolic cases. Our last joint paper with Mikhail Solomonovich, written in 2008, was devoted to such non-stationary problems. In particular, for this exponential of A epsilon, we showed that it converges to the exponential of A naught in the operator norm from the Sobolev space H3 to L2. And if we take such norm, we obtain sharp order estimate. the first power of epsilon on the right. So we realized that it is impossible to approximate this exponential in the L2 operator norm, like it was for the resolvent or for the parabolic semigroup. But we have to change the type of the norm. And in order to have the first power of epsilon, we should take the norm from H3 to L2. Also note that on the right, we have this factor, which linearly grows for large tau. And recently, in 2017, in my paper, it was confirmed that in the general case, this result is sharp with respect to the norm type. It means that we cannot replace H3 here by some HS with S less than 3. And quite recently, it was shown by Mark Dorodny, who is here, that in the general case, this result is also sharp with respect to dependence on tau. One cannot replace this factor by some power of tau which is less than 1. However, under some additional assumptions, this estimate 7 can be improved. First, it was improved with respect to the norm type, and recently by Mark, it was improved also with respect to the dependence on time. Under these additional assumptions, we can take here the norm from H2 to L2. Again, we have epsilon, and on the right, we have square root of tau for large tau. Later, I will explain what are additional assumptions. They are non-trivial, and they are formulated in terms of the spectral characteristics of the operator at the bottom of the spectrum. Similar results were obtained for hyperbolic equations. In operator terms, we studied this operator cosine of the square root of A epsilon multiplied by tau, and the corresponding sine multiplied by A epsilon to minus 1/2. These operators were studied also in our last joint paper with Mikhail Solomonovich. This operator was studied by Yulia Mishkova, and finally both were studied in our recent joint paper with Mark Dorodny. Now I will not speak about hyperbolic results in details, just mention. So what do we want to study now? We ask the following questions. Is it possible to approximate the separated exponential for A epsilon in the HSL2 norm with error of order epsilon squared using some corrector? And is it possible to approximate this exponential in the energy norm from some HS to H1 with error of order epsilon, also using some corrector? The answer is no. It is impossible. At least it is not possible to find such approximations in the same terms as before, in terms of the spectral characteristics at the bottom of the spectrum. And I hope to explain why it is impossible. What did we obtain? We obtained such approximations not for the exponential itself, but for this composition, for the exponential multiplied by this operator, identity plus epsilon lambda epsilon b of d pi epsilon. For this operator, it is possible to find such approximations. Then, what does it mean for the Cauchy problem? Such results can be applied to study the behavior of the solution of the Cauchy problem for the same Schrodinger-type equation as before. But we take initial data psi epsilon from a special class. We assume that psi epsilon, this is the sum of two terms, some function phi which belongs to HS with a suitable S, and this term, epsilon lambda epsilon b of d pi epsilon phi. Note that this operator is invertible. The inverse is identity minus this operator. So if we take psi epsilon for a given psi epsilon, we can find the corresponding phi, and we need that phi belongs to HS. Now, before we give formulations of the results, the exact formulations, it will be convenient to discuss the method because I need to introduce the necessary objects. These spectral characteristics of the operator at the bottom of the spectrum.
Why is the inverse operator of this quite simple form? It is the property of lambda.
Because the property of lambda, pi epsilon kills lambda. The mean value of lambda over the cell is equal to 0. Okay, so let us discuss the method, operator theoretic approach. It is based on the scaling transformation, the Flacker-Bloch theory, and the analytic perturbation theory. And the first reduction is the scaling transformation. By the scaling transformation, the study of this operator exponential for A epsilon is reduced to the study of the operator exponential for the operator A. A does not depend on epsilon. It is the operator with the matrix G of X. But here we have tau multiplied by epsilon to minus 2. Next, the operator A, which is an elliptic operator with periodic coefficients, can be expanded in the direct integral of the operators A of k. Here this tilde means unitary equivalence. The operator A is unitarily equivalent to this direct integral. The corresponding unitary operator is the Gelfand transform. The parameter k is called the quasi-momentum, so k belongs to omega tilde, which is the Brillouin zone of the dual lattice. And the operator A of k acts on the cell omega. It acts in L2 omega Cn. It is given by this differential expression. So we take the previous differential expression and replace d by d plus k. And this operator is considered on omega with periodic boundary conditions. Then we have to analyze this exponential for A of k. Also here we have tau multiplied by epsilon to minus 2. And we have to find approximation which is uniform with respect to the quasi-momentum k. And the main part of study is the study of this operator family, A of k. Which is an elliptic operator in a bounded domain, so it has discrete spectrum. We consider A of 0 as an unperturbed operator, and A of k for small k's as a perturbed operator. The kernel of the unperturbed operator is denoted by Gothic n. And this kernel consists of constant vector-valued functions. It is n-dimensional. So let it be the spectrum of the unperturbed operator. The point 0 is isolated eigenvalue of multiplicity n. And then we have other eigenvalues. By P, we denote the orthogonal projection onto this kernel. It's simply acts as averaging over the cell. For the perturbed operator, let it be the spectrum of the perturbed operator for sufficiently small k, the modulus of k less or equal than some t naught. Then what happens with this eigenvalue? On the interval 0 delta, we have exactly n eigenvalues counted with multiplicities. Lambda 1 of k, lambda n of k. This spectrum moves here, but from delta to 3 delta, we have nothing, a gap. And it turns out that for our problem, only this part of the spectrum is important. Of course, we control this delta and this number t naught explicitly, but now I will not write them down. It can be done. Next, we need to deal with one-dimensional parameter. So we write k as t times theta, and t is our main parameter, one-dimensional, the modulus of k. And theta is the unit vector. And we will write a of t and theta instead of a of k. We study this operator family by means of the analytic perturbation theory with respect to the one-dimensional parameter t. By the Cato-Rehlich theorem, there exist real analytic branches of the eigenvalues, lambda l's, and the real analytic branches of the eigenvectors, phi l's, of our operator family. The first n eigenvalues and eigenvectors. Of course, they are real analytic in T, but they depend also on the additional parameter theta, and we have to take care about this dependence. The set of phi l's forms an orthonormal basis in the eigenspace of our operator corresponding to this part of the spectrum. And now we write down the power series expansions for these analytic branches. They are very important, so I will write them down on the blackboard. The expansion for lambda L starts with a term of order t squared. The next term will be important for us, the term of order t cubed, and also the term of order t to the power 4. And these coefficients are strictly positive. They are separated from 0, which easily follows from the ellipticity. Next, we write down also expansions for eigenvectors phi L. They start with some embryos, omega L. Next, we have the term of order t, and so on. And the set of omega L's forms an orthonormal basis in the subspace of constants, in the kernel of the unperturbed operator. These coefficients are called threshold characteristics of our operator family at the bottom of the spectrum. Okay, next. Besides such power series expansions, we also need the so-called threshold approximations for the spectral projection f of k or f of t and theta is the spectral projection of our operator family corresponding to this part of the spectrum. We need approximation for this projection f of t and theta. Of course, it starts with p, which is projection onto the subspace of constants. Next, we distinguish the term of order t with coefficient f1. And we write down expansion for the operator A multiplied by this projection f. So for the part of the operator corresponding to this part of the spectrum. It starts with a term of order t squared. This operator S of theta is called the spectral germ of our operator family. Next, we need the term of order t cubed, and the remainder is of order t to the power 4. These operators f1, s, and k, they can be described in the invariant terms, and as well as in terms of the coefficients of these power series expansions. Let us look at f1. Here it is, b of theta is the symbol of b of d, and lambda is this solution of the cell problem, which was introduced before when I defined the effective matrix. Now S of theta, the spectral germ, in fact, it is the symbol of the effective operator. Here, G naught is the effective matrix. So in our approach, this effective matrix appears here when we calculate this spectral germ. And for the spectral germ, the coefficients gamma L are eigenvalues, the vectors omega L are eigenvectors.
What is the brackets?
The brackets mean the operator of multiplication by lambda of x. Next, the operator k, which is the coefficient of t cubed here. In fact, we do not need k itself, but we need the block of k in the subspace of constants. That is the operator n, which is k multiplied by the projection p from both sides. For this n, we have the following invariant representation. Here it is. And n can be represented also in terms of the coefficients of power series expansions. It is the sum of n naught and n star. N naught is diagonal in the basis of these embryos, in this basis. And the eigenvalues for n naught are the coefficients mu L at t cubed. The operator n star has 0 diagonal in this basis. N naught will be important for us. And only now we can formulate the results. We need all this to formulate the results. So first, we recall our old result with Mikhail Solomonovich, theorem 1. The exponential of A epsilon converges to the exponential of A naught in the operator norm from H3 to L2, and we have this order sharp error estimate. Now, new result, theorem 2. As I told above, we obtain approximation not for the exponential, but for the exponential multiplied by this operator. Approximation is given by the sum of two terms, the exponential of A naught and some character k multiplied by epsilon. Here, the operator norm is from H6 to L2. Then we have epsilon squared on the right, but we have this factor, which is quadratic in tau, for large tau. The character is written here. The first term is more or less standard character. which will be denoted by K1 on the next slide. The first term involves the exponential for A naught, B of D, multiplication by rapidly oscillating matrix lambda epsilon, and our smoothing operator pi epsilon. Also, we have the second term, and it does not depend on epsilon. Theorem 3. For the same operator, we now obtain approximation in the energy norm, which is the norm from H4 to H1. Then we have error of order epsilon, which is order sharp. On the right, we have this linear growth for large tau. And K1 is this character, which was the first term in the previous character. Let us discuss these results. First, we see that the characters K and K1 in theorems 2 and 3 are different, and this agrees with the results for elliptic and parabolic equations. Next, we see that the expected first-order approximation. Ask any specialist in homogenization what is the expected approximation for the exponential, and the answer will be this one, the exponential of A naught plus epsilon times K1. But this expected first-order approximation is not close to the exponential. It is close to the exponential of A epsilon multiplied by this operator in this norm. We think that it is impossible to approximate this operator, let it be the problem operator, in the terms of the spectral characteristics at the bottom of the spectrum. If we managed to approximate this operator, the exponential applied to this, then we will be happy, but we cannot do this. Why? If we apply the scaling transformation and next the direct integral expansion, we have to analyze this operator. Operator in L2 omega, here we have A of k, here multiplication just by the symbol B of k, and here multiplication by lambda. And recall that the mean value of lambda is 0, so the operator of multiplication by lambda can be written as P orthogonal lambda. P is projection onto the subspace of constants. And next, recall that the projection f of k on this part of the spectrum is close to P. So if we have the projection P orthogonal, within the margin of error, it can be replaced by f of k orthogonal. So we have to analyze this operator, exponential for A of k, multiplied by f of k orthogonal, where f of k orthogonal is the spectral projection for this part of the spectrum, for this semi-axis from 3 delta to infinity. And so it is no reason to expect that somebody can approximate this operator in terms of, in previous terms, in terms of the spectral characteristics at the bottom of the spectrum. Vice versa, we think that all the spectral, all the eigenvalues living here will contribute to the desired approximation for this operator. Of course, we jointly with Mark, we want to attack this problem, to try to find some appropriate approximation for this problem operator, but now it's an open problem. But we distinguished this problem operator. Okay. So, next results. Next results concern improvement of theorems 1, 2, 3 under additional assumptions. What are additional assumptions? It is condition 1. Suppose that at least one of the following assumptions is satisfied. The first variant is that the operator n of theta defined above is equal to 0 for any theta. The second variant is that n naught is 0. N naught, it was the diagonal part of n. N naught is 0. This is equivalent to the fact that all these coefficients mu l's are equal to 0. So we do not have here t cubed. In the second variant, we also need the following assumption, that the number of different eigenvalues of the spectral germ, that is the multiplicity of the spectrum, does not depend on theta. Note that, for example, for the acoustics operator, for the divergence type operator, where the matrix G has real entries, the first variant is satisfied. It is known that n of theta is 0. So this condition is not exotic. We have we know some other sufficient conditions when this condition 1 is satisfied. Theorem 4 is due to Mark Dorodny. Under condition 1, we have the following improvement of the result of theorem 1. Here, the difference of the exponentials, the norm from H2 to L2. In the general case, it was from H3 to L2. And another improvement, the dependence on time, not linear growth, but square root of tau on the right. And similar improvements concern theorems 2 and 3. Under the same condition 1, this is improvement of the result of theorem 2. In general case, here the norm was from H6 to L2, now from H4 to L2. In the general case, on the right, it was this term squared. Right-hand side grows as tau squared. Now we have linear growth. So improvement in two different senses. Next theorem, under the same condition 1, the result of theorem 3 is improved. Now here we have the norm from H3 to H1. In the general case, it was from H4 to H1. And another improvement on the right, we have square root of tau. In the general case, it was linear growth in tau. Finally, let us discuss the sharpness of the results. Roughly speaking, all the results presented today are sharp in both senses. This is the precise formulation. Theorem 7, the first part was proved by myself, the second part by Mark Dorodny. Suppose that at some point theta naught, the operator n naught is not 0. It means that at least one coefficient mu L is not 0 at some point. Then this estimate is not true if we take S less than 3. It doesn't hold. It means that the result of theorem 1 cannot be improved in this case with respect to the norm type. Second, suppose that here S is greater or equal than 3. It doesn't help. There does not exist a positive function C of tau growing at infinity slowly than tau, such that this estimate holds. It means that we cannot improve the result of theorem 1 with respect to time. And similar results are obtained for theorems 2 and 3 under the same assumption that at least one coefficient mu L is not 0. we cannot improve the results of theorems 2 and 3 regarding the norm type and regarding the dependence on tau. They are sharp. And finally, we show that the improved results that are valid under condition 1 are also sharp. Theorem 9, again, it's by Mark. Suppose that n naught is 0. For any theta, it means that all the coefficients mu L's are 0. And suppose that at least one coefficient mu L is not 0 at some point, which usually is satisfied. Then this estimate does not hold if S is less than 2. Which means that in the improved theorem is sharp with respect to the norm type. And second, let S be greater or equal than 2, then there does not exist a positive function C of tau, growing at infinity slowly than the square root of tau, such that this estimate is satisfied. Which means that theorem 4 is also sharp with respect to dependence on tau. And we have the same for theorems, the improved theorems 5 and 6. Under the same condition that all mu L's are 0, but some mu L is not 0, the results of theorems 5 and 6 are sharp in both senses, regarding the norm type and regarding the dependence on tau.